All right, so today we have Federico Bonetti tell us about symmetry TFTs from string theory. Take it away.
Well, thank you. Thank you very much. It's a pleasure to be given this opportunity to tell you something about this work in collaboration with Fabio, Iñaki, Sagar, and Sakura that appeared recently. So as you can imagine, I would like to start with some very general introduction. I think in a sense, especially to this audience, I don't really have to motivate why one-field theory is extremely important in physics, in all areas of physics, actually, and how important we therefore believe it is to us to understand as much as possible about the formalism of QFTs, ideally exploring regimes that are farther away from the more familiar, say, weak coupling perturbation theory. And we also know and appreciate very much the role of global symmetries in this endeavor. They're extremely powerful. They help us organize, say, the spectrum of the operators in our QFT. They give us word identities that constrain correlators in the theory. Sometimes they have Hooft anomalies, which are powerful observables, and many, many other applications. In a sense, all these ideas some of them are very old, but what has emerged more recently in the past few years is maybe a novel way of thinking about all these phenomena that really revolves around the idea of thinking of the global symmetries of a QFT as a sort of topological subsector of that theory. And one of the main advantages of this reformulation is that we can describe both older ideas as well as newer ideas in a unified coherent framework. And in particular, we can go beyond ordinary symmetries and discuss interesting generalizations of those concepts. So this is like a very short reminder of how this sort of shift in paradigm works if we have a continuous to one ordinary symmetry. The main idea is that instead of talking about a Noether current and its conservation, we think about a set of topological operators, these U operators, which are simply the integral of star of the current. And conservation is the same as the current being, as this operator being topological, invariant under small deformations of the surface sigma that supports them. And we can translate the familiar action of the symmetry on local operators as a topological statement, like in this picture on the right, where we have one of these U operators surrounding a point. And if we shrink it away, we act with the global symmetry on the operator curly O. And we also know that we can, since these operators are topological, we can move them to the point where they collide, and they give us another operator of the same kind. And in doing so, they satisfy a group law of this form. But once we reformulate these familiar observations in this more abstract language, it's very natural to consider all sorts of generalizations. We can play with dimensions and codimensions, and therefore have operators that are no longer just local, supported at points, but supported on lines, on surfaces, and correspondingly, the topological operators U that implement the global symmetry will also have various dimensions and codimensions. And perhaps even more exotic generalization, we can allow now fusion rules of these topological operators that contain, for instance, not just a single term, but a sum of terms, which therefore bring us away from the realm of group-like structures in global symmetries towards something more categorical in nature that has received a lot of attention recently. And there is another feature that I'd like to emphasize, and namely that it also turns out to be convenient to have a D+1 dimensional perspective. That's something I'm going to talk about in a moment. And one might wonder, why care about all these generalizations? In a sense, one reason is that they share nice features of ordinary symmetries. So for instance, we know that spontaneous breaking of global symmetries is a very powerful tool in organizing phases of QFTs. And the same holds true for some of these generalized symmetries. The prototypical example being that, say, one-form symmetries can be regarded as a diagnostic tool for confinement in gauge theories, for example. And then what turns out to be the case is that sometimes generalized symmetries have Hooft anomalies. If they don't have them, they can be gauged. But even if they have them, it's good news because those are observables that are necessarily matched across RG flow, for instance, and therefore give us powerful constraints on the various possibilities that we might have, for instance, for the phase diagram of a given model. And sorry, yes. And as I was mentioning a moment ago, there is in a sense one additional layer to this topological point of view on global symmetries, and namely that it's actually convenient in many applications to think of an auxiliary field theory that lives in one dimension higher. There's going to be this object curly A, which we may refer to as the symmetry field theory of the model we want to study. And its purpose is twofold. On the one hand, it's a tool to encode the Hooft anomalies for global generalized symmetries of the theory we want to study. But on the other hand, by slightly relaxing some technical assumptions on curly A, we can also use it to account for a more subtle situation in which our theory in D dimensions doesn't really have a single partition function when we put it on a D-dimensional closed manifold, but rather a vector partition function, which is a situation that occurs naturally actually in various cases. And sort of one important point that maybe it's worth emphasizing is that all these notions of generalized global symmetry and of symmetry field theory are completely independent on the existence or non-existence of a weakly coupled Lagrangian description for the D-dimensional theory we want to study. Of course, if such a description is available, it can be very useful in computing some of these observables, but their definition doesn't depend on it. And in many other situations, they can also be computed using other techniques. So this is the second.
Could I ask, is this topological field theory in D+1 guaranteed to always exist and encode the Hooft anomalies and maybe the relative field theory characteristics, or is it just known that in some cases such a thing exists?
I'm not aware of rigorous results that demonstrates that it necessarily has to exist, but I would say that the vast majority of examples that are usually considered fall into this category. I guess one could maybe argue for a general case for these objects in that thinking of the anomaly as a field theory in one dimension higher is a way, in loosely speaking, of encoding the locality of the anomaly, which seems on physical ground to be a sensible requirement. So it seems to be a very natural framework, and it accommodates for many situations. But strictly speaking, I'm not aware of a result that would prove that it's absolutely universal.
Thank you.
Okay, but indeed, in the situations we will consider, these objects are available, and in a sense, the philosophy of this talk would be to make sense of them and compute them in a situation in which we might or we might not have a Lagrangian description of the field theory. And in that sense, thinking about this problem in string theory is very natural, because we know that in string theory and in M theory, we can engineer vast classes of field theories. Some of them have Lagrangian descriptions, some don't, or maybe not yet. But the point is that that's, in a sense, we're using a different set of ideas to organize the space of field theories. We don't think about necessarily fundamental fields and their interactions, but rather we set up a geometry, maybe with some brain sources, and we use that as defining data. So from this perspective, a natural question in this field is, if we are given this geometric description of the field theory in string theory or in M theory, is there a way to use that geometric picture directly to extract as much information as possible on the symmetry and the symmetry field theory of the model we want to study, or of a class of models. And in this talk, I will be discussing how these ideas can be made more concrete if we look at M-theory on singular spaces. And we will see that the main idea is to consider the topological couplings in 11 dimensions and perform something of a dimensional reduction to a lower dimensional theory, which we then interpret as the desired symmetry field theory. And we will see that in order to keep track of some discrete symmetries that are really important for the kind of theories we want to study, it's necessary to keep track of torsional phenomena in cohomology. And this will constitute a technical challenge that we were able to overcome, resorting to this formalism of differential cohomology. So this was a general introduction. Before proceeding, I would like in the second part of the talk to say a few more words on why we think that symmetry field theories are interesting objects and say just a little more about them in general. And then I'll move on to the main part in which I'll describe how to extract the symmetry field theory using the geometric setup in M-theory for a class of examples. And then at the end, I'll have some conclusions and some future directions that are possibly interesting. Okay, so let's have a closer look at this notion of symmetry field theory. I'd like to start with some standard remarks on 't Hooft anomalies. We know that when a given quantum field theory in D dimension, I'm going to call it curly T, has a global symmetry, which might be an ordinary or a generalized one, it's very natural to couple it to a non-dynamical background gauge field. And here the terminology is a little loose. This could be a usual gauge field if we're talking about ordinary continuous symmetries, or it could be a slightly more sophisticated object like a discrete gauge field for discrete symmetries, or even something more abstract like a choice of orientation or spin structure on space-time. But let's be very schematic and denote all that collectively as A. So the point would be that we can couple our theory to this background and consider the partition function on in presence of a background. And as it's well known, the 't Hooft anomaly is the fact that if we perform a gauge transformation on the background fields, the partition function is not invariant. And we cannot simply cure this problem by adding suitable local counter terms in D dimensions. And we also know that on general grounds, the mismatch on the two sides is going to be a phase factor. So in other words, what one can say is that the partition function is not quite a function in the space of background fields, but rather it's more of a section of a non-trivial line bundle. And it is this second point of view that we can leverage to motivate a bit further this notion of symmetry field theory. So in a sense, this points out to work by Fried that revolves around the idea of thinking of a theory in D dimension that has a 't Hooft anomaly as a something called a relative field theory. So a theory in a sense that we may think lives on the boundary of a theory in a one dimension higher, and the purpose of that dimension is to encode the anomalies of the given theory. So in that sense, it's natural to call it the anomaly theory. And there is a more technical property of this theory, and namely that it's supposed to be an invertible field theory. Now, to properly explain this notion, we would have to go through the revisiting the definition of field theory as a functor between suitable categories. This is not really going to be needed for the purposes of this talk, but we can have an intuition of what's going on. So the expectation is that if we're given a field theory in D+1 dimensions and a closed D+1 dimensional manifold, it makes sense to evaluate the partition function of this theory. And in this case, the invertibility means simply that we get a non-zero complex number. And that number is actually a phase in the case of unitary theory. The other intuition we have in general is that if we have a field theory and we feed it something of one dimension lower, so in this case, D-dimensional, the field theory should give us a space of state, like the Hilbert space of the theory in that space. And in this instance, invertibility means that that has to be a one-dimensional space. The point, though, is that even, of course, every one-dimensional complex vector space is isomorphic to C, this identification might not be canonical. And in other words, what can happen is that with these complex lines, in a sense, vary in a non-trivial way over the space of background fields and form a line bundle, which is ultimately the line bundle of which the 't Hooft anomaly is a section. So in that sense, that's the purpose of the anomaly theory, giving us as space state this line, which then can be varied in a non-trivial way. And one might wonder, given this way of thinking about this, how do we recover the standard idea that there is a phase if we do a gauge transformation? And actually, there is a general recipe to do so, which I'm describing here schematically. And it's easier to describe if we make the simplifying assumption that our space-time, which would be M, can be extended, can be regarded as the boundary of another space-time U. And not just that, but all the relevant structures, for instance, maybe the spin structure or the gauge bundle, if there's one, they all extend to U. Now, if that's the case, we can consider a copy of U and a copy of U with orientation reversal. And now they have a common boundary M, and they can be glued along this common boundary. But before gluing, let us instead perform a symmetry transformation that here it's denoted schematically by phi. So what we can do, since phi is a symmetry, is therefore then glue on one side just M, and on the other side M acted upon by this transformation. And the final U phi d plus one dimensional manifold is something that now we can feed to the anomaly theory that will give us a phase vector. And the interpretation of this phase is precisely the anomalous phase that we would have, that we would find if we were to compare the partition functions on M and on M acted upon by the global symmetry phi. So the main idea in this, from this point of view, is to think of the field theory that we want to study as being relative to an auxiliary field theory, which is formulated in one dimension higher. Now, if we stick to the invertible case, that's perfectly fine to describe 't Hooft anomalies. But in some other for some other physical applications, it's actually useful to relax the invertibility assumption, so that, for example, it could happen that the space state of this auxiliary field theory on a closed d-dimensional manifold is no longer necessarily one-dimensional. It could have a finite but non-one dimension. And that, on the other hand, the notion of relative field theory tells us that the partition function of the T theory should be a vector in the space state of the curly A theory, which is to say that now we are allowing for the possibility of our d-dimensional field theory T to have not just a single partition function on a d-dimensional closed manifold, but rather a vector of partition functions. And this is a situation that arguably has first been studied and understood in 2D rational chiral 2D CFTs in connection to 3D topological theory, but then also occurs naturally in higher dimensions, I guess most notably in the case of interacting cis-D to zero theory, which are indeed relative theories in this sense. So the purpose of this review was essentially to remind you of these two main ingredients, the 't Hooft anomaly and the possibility of having a vector of partition function. And in order to account for both, we need to relax the invertibility assumption. And since in the literature, the terminology anomaly field theory is usually implied to always be invertible, that's why we prefer the terminology symmetry field theory, so that we can discuss both these aspects at once, if necessary. And also maybe a more technical point, let me maybe emphasize that this symmetry field theory curly A, actually it's not necessarily always a topological field theory in the strict mathematical sense of the word. And for example, there is such an object that we can use to describe the Hooft anomalies of an ordinary continuous symmetry, for instance, of a chiral fermion in 4D, arguably the simplest anomaly that we encounter first. And that five-dimensional anomaly theory, the so-called Dye-Fried theory, is not really topological. It depends on smooth data like a metric or a gauge connection. On the other hand, though, for all the examples that I will be discussing later on in this talk, we will be dealing with discrete symmetries. And therefore, it so happens that this theory curly A is actually a topological field theory. So that sort of justifies the maybe more, maybe simpler terminology, symmetry TFT for the objects that we would like to discuss in what follows. And it's probably now a good time to have a look at a concrete example. And from a gauge theory perspective, it might seem like an odd choice, seven-dimensional Super-Yang-Mills theory. But I'm motivated in this choice because that's arguably one of the simplest examples from the geometric engineering point of view that we will see later. So let's have a quick look at this case. The field theory itself is nothing particularly exotic. Let's just say it's a Super-Yang-Mills theory with gauge algebra, say, for instance, SUN. And now, of course, we know that there are different choices for the global form of the gauge group. And in a sense, at least loosely speaking, if we are agnostic about the form of the gauge group, and we only consider the algebra, we are, in a sense, talking about a seven-dimensional relative field theory. And relative to what? Relative to a special 8B TFT of a sort of famous type, a BF theory, which can be described in the continuum by this action written here. And here the main point is that this TFT is not necessarily, it's not actually an invertible TFT, at least for n larger than 1. And indeed, one can verify that the space of states that this TFT associates to a 7D closed manifold, it's not necessarily of complex dimension 1. And the intuition between the relation of this 8-dimensional TFT and the choice of the global form of the gauge group in 7 dimensions is that we can choose different topological boundary conditions for this BF theory, and they result in different 7-dimensional choices for the global form of the gauge group. So the simplest two examples are just to give, say, for instance, Dirichlet boundary conditions to the 2-form field, B2, and just free boundary conditions for the other. In this case, we land on gauge group SUN, and the 7D theory has a global one-form symmetry, the ZN one-form symmetry. At the opposite end, we can consider instead Dirichlet boundary conditions for the 5-form C5, and we would land on a PSUN theory that has a dual magnetic 4-form symmetry. And these are not the only two options. For instance, if n is written as a product of two integers, we can also consider mixed boundary conditions that will land on a mixed 1-form, 4-form symmetry in the theory. And so this is about the, if you wish, the non-invertible part of the story is a concrete example of that. And as far as the Hooft anomaly part of the story goes, well, since we are in odd dimensions, clearly we don't have Hooft anomalies of ordinary continuous symmetries of the usual kind. But there is one specific anomaly that we will be particularly interested in. And that is mostly easily seen if we choose the global form SUN for the gauge group. Because then, as I mentioned, we have a global one-form symmetry, ZN, and the boundary condition for B2 is itself the background field for that one-form symmetry, which then becomes in the discrete description, a cohomology class with ZN coefficients. And this gauge theory, however, also has a continuous U1 2-form symmetry, which we might refer to as instanton symmetry, in that it is it has a current that it's topologically conserved because it's simply the 7-dimensional Hodge dual of the essentially the C2 or P1 of our gauge field. And we can clearly, if we so want, couple this J3 to some gauge field, little c3, which is continuous, but it's a 3 form. And the point is that there is a mixed anomaly between this continuous instanton symmetry and the ZN1 form symmetry. And that can be encoded in a term in the topological action in 8 dimension of that form, which was derived sort of systematically in a 4-dimensional analogous situation by these authors, considering also other algebras, not just SUN. So in a sense, these are precisely the objects we are after. Our goal would be to try and reproduce the ideally both, namely both BF terms that lead to not necessarily invertible theories in 1 dimension higher, as well as anomaly terms which indeed do instead lead to an invertible field theory. And as, of course, this was just an example, but you can imagine many other different situations. And these are the kind of objects that we would like to be able to compute in a systematic way, and which is ideally as general as possible. Okay, so I think that, yes, that is the end of this sort of motivational part. Now we can indeed go to the main part of the talk, and namely ask ourselves, how do we make all these ideas more concrete in a class of examples? And in particular, I will be considering M theory on a singular space. So this is this kind of, if you wish, compactification on a non-compact space that leads us to lower dimensional theory without dynamical gravity, which in the case in which the internal space is of the form C2 mod gamma, where gamma is an ADE subgroup of SU2, it's precisely a 7-dimensional super-Yang-Mills theory with a corresponding Lie algebra. Whereas if we consider a more interesting internal space, such as a canonical threefold singularity, then we can consider vast families of non-trivial SCFTs in 5 dimensions. Now, some of these 5-dimensional models may or may not admit a mass deformation that leads to a Lagrangian description in terms of a non-abelian gauge theory in the IR. But our goal, our task is to find ways to compute these anomalies that don't rely on this non-abelian Lagrangian description. And we will see how that is indeed the case, how that is possible. And as a side note, here I'm going to emphasize in these geometric engineering setups without brains to highlight the role of torsion. But clearly this program, more sort of from a larger perspective, can be carried out also for theories that are engineered by string theory or M theory setups that have brains. And in that context, it's also possible to access both terms of BF type, so sort of non-invertible terms, as well as more traditional Hooft anomalies. And this, for instance, can be done using an anomaly inflow paradigm that is inspired by the seminal work on the anomaly inflow on M5 brains in 6 dimensions. Okay, but let's stick to this more geometric engineering idea. And we just consider M theory, no brains, and we have a singular space. And actually that singular space, in all examples we want to study, is a Calabi-Yau cone. So there is a well-defined notion of a link in 1 real dimension lower. And therefore we have a schematic situation like it's depicted here on the top left. And we can also have a very concrete description of the link geometry. In the simplest example of C2 mod gamma, it's just literally a 3-sphere mod gamma. And in the case of the Calabi-Yau cone, essentially by definition, the link is going to be a Sazakian 5 manifold. And many interesting examples of those are known, of course. Now, as our main point is to compute topological couplings. So that observation gives us a heuristic picture on what might be a good strategy to access those. And namely, we can leverage the idea of those coupling being topological and imagine a deformation of space-time of the kind depicted on the top, in which, in a sense, we modify the asymptotics. It's not really a cylinder anymore. We just take it to be constant, like a sort of cigar configuration. And in a sense, we can even think of imagining to sort of reduce the size of the link space. And as you can see, the cigar, roughly speaking, turns into a half line. And this is a heuristic way of seeing the emergence of this topological theory that lives in one dimension higher and that admits our physical theory as a boundary condition. And with this philosophy, namely dimensional reduction on the link, we can reconstruct both terms of BF types as well as Hooft anomalies. In order to do so, we have to use slightly different techniques. And for this talk, I would rather focus on the Hooft anomalies. In case you are interested in knowing how the BF terms can be derived, I'll be happy to explain in case there is a question. But I would say for this moment on, we will be focusing on anomalies. So if you reach the invertible part of the story. Okay, so we have this sort of idea that it might be good to do a dimensional reduction on the link, but then what should be our starting point? Well, there is another natural candidate, and namely the couplings that we see in 11-dimensional supergravity. There is the two derivative CGG Chern-Simons, and there is also a higher derivative correction whose role is really crucial in making sure that the theory in low energies is well defined. Namely that the path integral of 11-dimensional supergravity is well defined. And this will be our starting point to perform a dimensional reduction a la Kaluza-Klein, in that our field will be the three form of M theory, and we will be expanding it schematically in internal forms, so to say, in our link geometry. And the coefficients of this expansion are going to be gauge fields in external space-time, which we interpret as the background fields for global symmetries of the QFT that we want to study. So what we can see is that if we have this starting point in 11 dimensions and we dimensionally reduce on the link, we indeed land on a topological Lagrangian in 12 minus d dimensions, which we interpret as the action of the symmetry field theory of the QFT that we want to analyze. So this is a well-tested, say, also recipe in other contexts, say also in holography. The point that we face here, maybe it's not as much as a necessarily conceptual point, the idea of reducing on the link, but maybe a more technical difficulty that we might face. And namely that discrete symmetries are really the most interesting ones. And therefore we have to have a way of describing torsional phenomena. So let me elaborate a little more on that with an example. For instance, the case of 5-dimensional superconformal field theories. There are general arguments that allow one to compute what the one-form symmetry group of the theory is using the geometry of the say the Calabi-Yau space X and of its link, the boundary of X, in terms of relative homology. And the point is that these one-form symmetry groups are all discrete, and we can identify them exponentially with the torsional part of the integral cohomology of the link space. So in order to make an advance, computationally speaking, in order to perform this dimensional reduction from 11 dimensions, we have to identify a way that is precise and sort of general enough to deal with torsion cycles in our supergravity description. Now, this is clearly a problem that has received attention in the past, and there are indeed several approaches that are possible. Some of them, for instance, as in these papers, rely on a description in terms of non-closed differential forms in our internal space. So while these descriptions have certainly been useful for discussing various aspects of string theory constructions in the past, in this specific instance, we felt that using the formalism of differential cohomology rather than using differential forms was better suited, basically because it's at the same time a sound mathematical framework, and also it can be implemented in a quite general way. So it's also, in a sense, quite flexible, whereas sometimes using these non-closed forms can be harder to apply in a systematic way to different setups. So having somehow motivated why the tools of differential cohomology are of interest for this sort of problems, let me now say a few words about differential cohomology in general. Of course, I mean, this is quite an important subject, both in physics and in math, and we'll not really be able to summarize it and do justice to it in a few minutes. So let me essentially just highlight what are the points that are most relevant for what we would like to do in what problems. So first, I'd like to just set up some notation. I'm going to use always these little hats on top of objects to refer to differential cohomology. And in particular, the 4H hat is the group of differential cohomology classes of a given degree P. And we can think of it as the differential refinement of the integral cohomology group HP. And in physics terms, an element in this space is actually a very natural object in that it models a continuous U1 field, except that instead of being a one form gauge field, it can also be in general a P-1 gauge field, depending of course on the degree P. And here, sort of like to help also the mnemonics, the degree refers to the degree of the field strength. So this the one gauge field in this example will have a P-form field strength. And as we know, because of Dirac quantization, the fluxes are going to be quantized. In a sense, that's an intuitive way of seeing the connection with the integral cohomology group that, in a sense, is measuring the fluxes for us. And there is, in particular, there are several, of course, operations that we can perform on these differential cohomology classes. There is one in particular, which in a sense is forgetting about the differential refinement and going back to integral cohomology. And this is a map I'm calling here big I. And the main fact that will be important later for us is the observation that this map is actually surjective. So that in particular, we can take our favorite integral cohomology class, and we can always uplift it or promote it to an element in differential cohomology, which though may not, is necessarily not unique, but nonetheless it exists. Okay, so now we have these A hat objects. What can we do with them? Well, it turns out that there are some operations that have a very strong formal analogy with more familiar operations with differential forms. For example, there is a well-defined
Sorry, can I ask a question about the previous slide?
Sure.
So you say if I can think of those elements as you want gauge field roughly, how do you implement the fact that you will discuss a discrete group? Is it just changing some other coefficient in the map at the bottom, or if I have a Zn gauge field, for instance? Okay.
Thank you for the question. We will see that we will stick to this description, which is indeed engineered or sort of more naturally geared towards U1 gauge field, but we will be able to use it to also give a description of discrete fields. So we don't really have to change the coefficients. We can use this version, the standard version, to also describe discrete background fields. And I will discuss that in a few slides. And in case, of course, you're always welcome. We can revisit this point.
Thanks.
Okay. Also, yeah, maybe it's worth mentioning, as you can see, I haven't given you a definition of what these A-hat elements are. And in a sense, that's also because there are different models for differential cohomology, and some of them have are best suited for some applications. But nonetheless, there is also a model-independent description in that we can always work with operations that mathematicians have demonstrated to be well-defined and obey certain rules. And luckily for us, these operations are quite similar to more familiar and more elementary operations that we use all the time. One of them is the product in differential cohomology, and it's in a sense exactly what you would expect from the wedge product of forms. It preserves the grading, and it's graded commutative in the usual sense. And then there is also a notion of integration. And in a sense, here comes a surprise that will be really important for what follows. Namely that, of course, we know that if we're talking about differential forms, we have to pick a form of top degree in order to be able to integrate it on our manifold. With differential cohomology classes, we have actually two options. The first, which is sometimes called the primary invariant, is the direct analog of the integration of forms. Namely, we pick a class whose degree is the same as the dimension, and we integrate. And in this case, the answer is an integer. However, we now have a second option, and namely consider a class a hat whose degree is one unit higher than the dimension of our space. And we can still nonetheless make sense of this integral. And in this case, the integral though is no longer just a real number, but it's actually an element of R mod Z. Or if you wish, of course, you can exponentiate and think about that as a phase. So let me illustrate both these elements, the product and the integration, in one simple example.
So maybe I can, so these are just like integrating the field strength or integrating the gauge potential. Are these two different invariants? If we're thinking, let's say, in terms of some U1 N form gauge symmetry or something like that.
So indeed, for the primary invariant, we can think of this integral as, if you wish, we can act with I. Remember, there is this map that forgets the differential refinement. And then the primary integral is just the integral of the class in integral cohomology. For the secondary invariant, let me briefly discuss this example, which maybe might also help clarify this point. Like, how should we think of these secondary integrals? But yeah, I guess in a sense, loosely speaking, we can indeed think of them as holonomies. And in this example I have in mind here, I'm thinking of a situation where we are in 3 dimensions and we want to describe an abelian U1 gauge field of one form of the usual kind, which in physics we would denote something like A. Think about that as a one form. In this language, though, we model it with a differential cohomology class of degree 2, 2 being because its field strength is a 2 form. Now there is this product operation. We can take A star A, and then we land on an object of degree 4. And thanks to the integral operation, we can actually perform the integral in 3 dimensions and get this secondary invariant. And this is actually nothing but what we would write more traditionally as A wedge dA. The advantage of this formulation is that, well, for instance, say that I give you a flat connection. Then if you take the A wedge dA expression literally, you might conclude that this is 0, just because dA is 0. But that conclusion is too naive, because it could be that while flat, the connection A is topologically non-trivial, so that this A dA expression is only valid locally. And in a sense, all the interesting stuff is happening on how different patches are glued together in our manifold. And so this A star A on M3 is a compact and mathematically sound way of encoding this information. Okay, so I think essentially now we have, in a sense, all the ingredients to set up this reduction that we would like to perform. Space-time for us will always be a product of an unspecified external space-time, unspecified in that we would like to put our field theory on different spaces, if we so wish, and a fixed internal manifold L. And if we were doing a regular KK expansion, we would say something like, consider harmonic forms on your internal space. They give you massless modes externally. And in a sense, there's a connection to this that we have discussed before, because we know that harmonic forms are in one-to-one correspondence with the RAM cohomology classes. And we also know that there is flux quantization, so we should actually be considering harmonic forms with integral periods in our internal space L. And all of this means that we're, in a sense, expanding onto integral cohomology classes, but necessarily only the free part of those, because if the class is torsional, it cannot be represented by the RAM cohomology class. So the point is precisely to capture this torsion part. And luckily for us, as I mentioned earlier, there is this map I, which is surjective. So it means that we can pick any class, let it be torsional or non-torsional, and uplift it to an element in differential cohomology. And it is essentially this observation that gives us now a systematic recipe in that we can start modeling the C3 gauge field, so to say, of M theory as an element of degree 4, just because it has a 4-form field strength. Then we can study the integral cohomology of our internal space. In general, in various degrees, it might have free part and a torsion part, and we can pick, say, a generator for each of those parts. And we can now promote all of them to elements of differential cohomology and use them to expand G4. And now maybe here it's very briefly just a word of caution. In a sense, it's an approximation to think of the M theory 3 form as an element in integral cohomology, in that we actually know from string theory considerations that the correct thing to do would probably to start with a more sophisticated cohomology theory and do the integral and do the differential refinement of that. So that's an interesting point. Luckily, though, for the applications of the rest of this talk, this approximation with integral cohomology and its refinement is going to be enough for us to get to some interesting conclusions. Okay, so how would this work in our simplest example? So let's say we consider M theory on something like C2 mod Zn. It could also be C2 mod gamma, but let's stick to Zn for definiteness. So the link in this case is just essentially a length space as 3 mod Zn. And here are its integral cohomology groups with a choice of, I'm just giving a name essentially to the generators of these groups. So there are 2 non-torsional ones. They're a little boring. It's just 1 in the volume form. And there is a torsional element of degree 2, T2. So the idea is now that all 3 generators will be uplifted to elements in differential cohomology. So they have little hats. And then we do an expansion of G4. And the coefficients, so to say, of this expansion are also differential cohomology class, but of external space-time, W8. And of course, we just have to match the degrees. So we're going to find something of degree 4, something of degree 2, corresponding to the torsional part, and something of degree 1. And what is the interpretation of these objects? As I anticipated, they are external gauge fields. So if the rule of is as follows: if you are expanding on a non-torsional class, like here it would be 1 or V3, you get a continuous external background field, and the degree that you see here is the degree of the field strength. So in this example, we'll find therefore something that has to do with a 3-form gauge field from gamma 4 and a 0-form gauge field, an axion for F1. And in field theory interpretation, I have already actually mentioned gamma 4 is this background for the instanton 2-form symmetry, whereas this F1 seems to be related to something like an anomaly in the space of coupling constant. So something whose field theory interpretation is a little more subtle. And then there is the other half of the story. If you are expanding on a torsional element, what you see outside is a model for a discrete gauge field. Now, as a mathematical object, it's still a class in differential cohomology, but the physical interpretation is in terms of a discrete gauge field with an order n, which is precisely the same as the torsional order of your generator. And maybe just to be completely precise, here we are assuming that external spacetime has no torsion. So all the torsion is internal. So to describe, for instance, a background field for a Zn symmetry, we can always think of an integral class and reduce it mod n. And this reduction mod n is automatically implemented for us in this construction. In a sense, that's how B2, which is still with Z coefficients, if you wish, is describing something with Zn coefficients, because we are only considering it modulo n. Okay, and now the final step, we have an ansatz for G4, we have an action. This is the same as before, it was written as CGG, now it's just rewritten in this language, in which is like G4 cube, which is something of degree 12, we can integrate it on 11 dimensions. And what we have to do is just to collect the terms that can contribute, keeping in mind that we have both primary and secondary invariants. So if the total internal degree is the same as the dimension of L, this is a more standard primary invariant. But now we have this other option of having an internal degree which is 1 unit higher, which could give us a secondary invariant. So in the example we have here, G4 had this form, we can plug everything in, and there are only 2 terms that survive. In one of them, the internal part is very straightforward. It's just the integral of the volume form on our space. And it is the coefficient of an anomaly with just continuous ingredients, this instanton symmetry and this, if you wish, -1 form symmetry in quotation. But the object of interest is actually this other part. This is the anomaly between the instanton and the Cn1 form symmetry that we would like to study. And its coefficient is actually a secondary invariant. It's precisely this sort of A wedge dA kind of thing that we saw earlier. So our task now is precisely to compute this object, because if we are able to do so, we get the 12th anomaly coefficient that we would like to derive. So how are we going to do that? Well, in a sense, that if there was no 1/2 in front, one can prove in general, sort of chasing the definitions of the product in differential cohomology, that this operation would be the same as the linking pairing. The linking pairing is a standard operation that you can do on torsional classes. It's sort of the analog of intersection numbers. And it gives you a rational number mod 1. So our problem here is that we have to compute this object, which is more refined because there is a factor of 1/2 in front. And indeed, this object, for example, depends in general on the choice of spin structure. And there is no obvious way of choosing which one of 2 possibilities are realized when you try to compute this object dividing by 2 in a naive way. So to find an unambiguous way to compute this object, we have resorted to an approach explained by Gorthon and Litherland in the math literature. The idea would be to fill in our link geometry and think about that as being the boundary of a 4-dimensional space. Of course, for us, this is extremely natural. In M theory, that's exactly what we had, the non-compact C2 mod Zn space. And for the purposes of the computation, is actually more useful and important to consider a resolution of this so that we have a smooth space. And now comes the main observation, and namely that we are given a torsional class on the link geometry on the boundary. By Poincare duality, that's the same as a torsional 1 cycle, and that can be uplifted to an element in the homology of the filling, but not the relative homology, or in other words, it can be uplifted to a compact 2 cycle that I would be denoted in big Z. And now the main idea of the Gordon-Littleton approach is that if you want to compute the secondary invariance on the link, you move to the filling, and there you have to do a more traditional intersection theoretic computation. You compute the intersection number of this compact two-cycle with itself inside the filling space as x4, and then you divide by n squared, and you reduce mod 1. And here, sorry, probably this integral was not necessary. It's implicit when you take z dot z that you're getting an integral number, which is the intersection number. And this prescription is flexible in that you can use it to recover the known results about linking pairing here on the left, but you can also use it for the case that we are interested in, this refinement with the 1/2 factor. And let me skip this. We can get a very concrete answer for the example that we have at hand, because in that case, we know what this big Z is. It is a specific linear combination of the resolution two cycles that we encounter when we resolve the C2 mod Zn singularity. And actually, in the canonical basis, this is a very simple linear combination with coefficients 1, 2, 3, 4, and so on. And in this basis, we also know that the intersection pairing of compact two-cycle is literally the opposite of the Cartan matrix of SUN. And therefore, this Z.Z object can be computed easily for any n, plugged into the formula and giving us the desired anomaly coefficient, which, as you can see, includes precisely this -1/2 factor, which maybe one could have missed if you just take 1/n linking number and divide by 2, sort of naively. And also, importantly, for the self-consistency of this, it was rewarding for us to see a perfect agreement with the purely field theoretical analysis of these authors, which persists also not just for SUN, but for all the ADE cases. And now that sort of we have tested this in 7 dimensions, we can apply it to many more examples in 5D. And the recipe is essentially the same. We have to compute the cohomology of the link, L5, and this could have both torsional and non-torsional contributions, expand G4 appropriately, plug everything into the 11D action, and find the invariants on L5 that we have to compute. The interesting ones are, again, secondary invariants, and we compute them with a variation on this Gordon-Littleton method, mapping the problem to a problem of intersections of compact cycles in the filling of the link. And in that sense, this is similar to the Coulomb branch approach of this paper, but in a sense, it's also distinct from it in that our idea is that we have to compute the secondary invariant. And the filling for us, it's more of a tool to do the computation. But we don't necessarily have to go to the Coulomb branch, say, of the model. And let's have a very quick look at one class of examples. Let's say that our link is a famous Sasaki-Einstein manifold, the YPQs. And it is known in that case that the 5D SCFT admits a mass deformation that gives us SUP gauge theory with chain signals at level Q. And there is a discrete one-form symmetry whose order is the GCD of P and Q, and a continuous U1 instanton, which is now a regular zero-form symmetry. And again, we can ask about mixed anomalies involving these. And here I'm just sort of flashing very briefly what happens. In this case, the relevant cohomology group is, again, in degree 2. The only novelty is that there is not only a torsional generator T2, there is also a non-torsional one. And the torsional one has to do with the one-form symmetry, and the non-torsional one has to do with the instanton zero-form symmetry. And now, according to the Gordon-Littleton procedure, we have to consider the space that fills the link, so the Calabi-Yau threefold, and actually its resolved version. But luckily for us, this is a toric model, so these computations can be performed in a very systematic way, even though clearly one can also consider non-toric models. That's not a requirement for this formalism to work. And what we can see here, the details are not terribly important. I just wanted to flash a couple of equations to show that everything is very computable, very concrete, and we get answers for these Hooft anomaly coefficients as functions of the P and Q data that match precisely with a field theory computation that was done by other methods.
You should probably cite Pietro and Luigi there, right? Who computed the B squared F.
Oh, indeed.
First,
thank you.
right?
That's true. Absolutely.
I see Luigi there. I don't think this is okay.
Thank you. Yeah, sorry for the oversight. Yes, so it was sort of like nice for us to see that we were able to do this case, but in a sense, the fact that this was a gauge theory SUP at level Q, it doesn't show up directly in the computation. And indeed, we can perform very similar computations for other models, for instance, these BN and BNI models that are non-Lagrangian in the sense that they don't admit this description as a gauge theory with a non-abelian gauge theory. And nonetheless, these anomaly coefficients are well-defined and are accessible using this technique. Okay, so I'll go to some brief conclusions. So I hope I convinced you that this notion of symmetry field theory is something useful and interesting that we can look at. It knows both about Hooft anomalies as well as more subtle phenomena like being a relative field theory with a vector partition function. And in the framework of geometric engineering, we have demonstrated that one can do a sort of Kaluza-Klein reduction of topological couplings, including torsional elements in the internal space. In a sense, this M-theory construction are just an example. We could consider other dimension. We can try to apply it to F-theory using F-theory to M-theory duality. It's also natural, I would say, to combine these more torsional elements of the story with something more inflow-oriented, thinking about brain sources in brains in string theory and M-theory, and hopefully even go beyond and, for instance, combine isometries and torsional phenomena, maybe using equivariant versions of differential cohomology that are known to exist in mathematics. And finally, one might be able to also uncover more subtle structures that are known to appear in field theory. For example, higher group structures in like these CFTs. It would be quite interesting to see what their counterpart is and whether it involves torsional phenomena. And with that, I'll finish.
All right, let's thank Federico for this talk. And do we have questions?
Well, I have a, well, unless they're more relevant questions, I have a question which is not quite in the main point of your talk. Early on, you mentioned that the anomaly field theory need not be a topological field theory for some examples of continuous symmetries, which kind of confuses me. I would have thought for a unitary theory, I wouldn't want to couple it to a higher dimensional theory with propagating degrees of freedom. Or maybe I'm misunderstanding.
Maybe, yeah, let me comment more on that example, actually. I think I might have it here. In which sense I was referring to it as non-topological. So this anomaly field theory is a gadget in this case that when you evaluate it on a closed manifold, it gives you the exponentiated eta invariant. And all I was pointing out is that this mathematical object, the exponentiated eta invariant, varies smoothly when we vary the metric and the gauge field. So in that sense, probably mathematicians wouldn't call it a TQFT in the strict sense of the word.
So you're saying it depends on the diffeomorphism class of the metric, as opposed to the topological class of the manifold, but it's still diffeomorphism invariant. So it doesn't have, it's not what physicists would call being sensitive to local excitations.
Yes, I would think that's right. See, indeed, in a sense, it's still gauge invariant, but it will know more than just the topology, indeed. And to me, one way to see that a bit more directly is this application of the APS theorem. So if your 5D space is the boundary of something in 6D, this eta invariant becomes essentially an integral of the anomaly polynomial on a space with a boundary. So here I'm thinking that I can maybe do let's say a little change in the connection for the gauge field. And since now W has a boundary, that would modify the result.
I see. Thank you.
So here it's a classical theory, right? Anyway, I mean,
Yes,
so it just so happened it's not like a Chern-Simons term, which would be also often classical background Chern-Simons in D+1 for some anomalies. Here more generally is the eta invariant, but it's a classical field theory, just a function of background field that you extend to 5D, right? Am I understanding correctly?
Yes, that's right. It's classical.
There is no degree. You don't need to do any path integral anyway. So, you know, calling it field theories. Yeah. Okay. Thanks.
That's true.
Okay. Do we have more questions?
Yeah, I have a question. When you do this geometric engineering, let's say in 7 dimensions, when does it come, you know, like the choice of the global structure of the gauge group? So basically, I mean, what would you say that we get if we put M theory on this C2 mod gamma? Then you always have to specify this B2 or C2 boundary conditions, or?
Yeah, in a sense, the picture that emerges is that the degrees of freedom that are localized at the singularity are those of the relative theory, if you wish. And the choice of global form of the gauge group is all about the flux at infinity. In a sense, the way to argue for that is to observe that the torsional fluxes, say of G4 and G7, are non-commuting in 11 dimensions, and therefore, in a sense, they cannot be, loosely speaking, all diagonalized simultaneously. And in particular, you cannot set all the torsional fluxes at infinity to 0. And there is a choice to be made, essentially of a maximal set of commuting torsional fluxes that can be specified. And one can map that choice of flux at infinity with the choice of global form of the gauge group for the theory.
So just to understand, you must specify it anyway. Like it's not enough to say you put M theory on C2 mod gamma.
No, in a sense, yes. One should probably regard the choice of torsional flux at infinity as part of the definition of the M theory setup.
Okay, thank you.
Okay. Do we have more questions?
Can you say more about how you do the filling in the 5D example? So you're saying you have a 5 manifold, you complete to then what the resolve Calabi-Yau?
Yeah. And the idea would be to use the resolved version of the Calabi-Yau cone itself.
And so then you need to evaluate similarly to what you explained for the Chern-Simons theory. So you will need to evaluate whatever f wedge or whatever in the 6D. Or do you do that concretely, or is there like a mathematical result that you were using to get those 1 over GCD cubed and stuff?
Well, this is like the natural generalization of this result of Corathon and Dieterle. So they proved rigorously that you can get the linking pairing by intersection theory in the filling. And this 1 over GCD, it's part of the prescription. Essentially, it's sort of easy to remember. You just divide by 1 power of the torsional order for every power of Z that you have in the numerator. So that's a sort of well-established mathematical results. And what we have done is to use its natural generalization, and it has worked very well in reproducing the known field theory results.
So it's a conjecture really here and in 6Z.
I guess, yes, technically speaking. It could be that it has been also proven in the mathematical literature. I'm not aware of that. So yes, it could be that as of now, it states as a mathematical conjecture.
Okay, thanks. Thanks for the nice talk.
So why are you saying this conjecture? I mean, these intersection numbers are just calculated. Z is a combination of compact divisors, and they are determined by the resolution. And
no,
you're asking about the 1 over GCD.
All I was pointing out is that this, how should I, maybe this recipe here, sorry about the typo, there shouldn't be an integral. I'm not aware of a rigorous.
There's no Born-Little-Like theorem for Calabi-Yau threefolds.
Yeah, that's all I'm pointing out. Yeah.
But then there's also good arguments in terms of just gauge invariance and so on. And also the fact, I think, that we can calculate again from the link topology what this one-form symmetry is, or the degree of this one-form symmetry is. That also fixes why there's a GCD in the denominator. Right? Why this is a form field. What you actually get directly is sort of not the thing divided by 1 of the GCD cubed, but just the intersection number, right?
No, I mean, I completely agree. Like, why there should be GCD here, precisely, it's because of the order of the one-form symmetry, and that's totally unambiguously computed by the geometry. Same for the Z cube. The only part that maybe has not the status of a rigorous mathematical theorem is the prescription that if you compute this into this rational number, you take it mod 1, that's the same as this secondary invariant in differential cohomology. That's all I was pointing out.
Sure.
But I'm very confident that this is the correct picture because it passes several non-trivial consistency checks.
I mean, this is not a math seminar, it's a physics seminar on physics terms. I think it's something that's computed rather than saying this is a conjecture. Maybe one comment, since I think this is like probably an audience where half of the audience works in brainwebs, there's a way to really see these anomalies also come out of the webs. And I think that's sort of Fabio's specialty. So he's, I think, left. Maybe he'll talk about that in Aspen.
Oh, that's very nice.
Because I mean, there's a sort of really counterpart to see how you get Hooft anomalies or this Sim TFT directly from the boundary of the brainweb. So I think that might be actually interesting for half the audience at least.
So P mentions divisible 2, GCD2 is also divisible.
Do we have more questions for Federico? All right, so then let's thank Federico again. Stop the recording.